Yeah. So the last time, so we did clustering and naive, right? So the naive, did you able to load it in your system?
Means I worked with this file which you sent me. Yes, I did that.
This is bit like there is an individual program I also we discussed, right? But I didn't share that. So TF idea vectorizer. So when you
Mhm.
do it, you'll be able to know how it is getting.
Yes, yes, that I was able to do it. Yes.
So today we are going to discuss again unsupervised learning, and that is different. That is called PCA. So,
Mhm.
so we are going to discuss that. Just want to show you something before it. Sorry. So when you did here, I added the 3D view. So might be that is also sometimes you'll be requiring. So
Okay.
so that day you put at a 2D map, right? So this one.
Mm-hmm.
So this is a 3D representation of the data.
Data. Okay.
So I will send this piece of code. So this is the import matplotlib import for 3D.
Okay.
And in the scatter plot, we put 3 columns instead of 2.
Okay.
And these are the 3 centers. C is a Y mean. So Y mean is this. Okay, this is not sorry. Y mean is the, this one, the target predicted value. Clustering
Mm-hmm.
whatever it is found, 1, 0, or 2, which 3
Mm-hmm.
types, not of predictions, but a grouping.
Mm-hmm.
So that has to be supplied. So that has been colored here in the 3D map. So I'll send you
Yeah.
this one to you.
Okay.
So the other guy is always off. I think I don't know. Today, so yesterday he was attending class. Today again, I is missing. Okay,
Okay.
I'm sending the video to him.
Mm-hmm.
So they are student actually. So they're very much. So he's an MTech guy in MSc in computer science from some Malaysian college.
Okay.
So, but sincerity is a little bit less. I think what to do. That's okay.
Mm-hmm.
So principal component analysis is what is used for actually.
Mm-hmm.
If you see some data now, whatever we have seen, some sample data have only 10 or 13 columns, right? Features. So it can be very big, thousands of more than thousands, 3,000,
Mm-hmm.
5,000. So that time you cannot, I mean, do the analysis. So why? Because giving an example, like that they was working on something. Uh, so there is like one way I showed you in right regression problem that if there is a two features, one features, the dy by dx will work, right? If there is a free z is there, then dy by dx, right? So the
Mm-hmm.
linear regression how it will work? Dy by dx into x variable plus dy by dz into again x2 y variable, right? Second variable. So did you able to interpret it? So let me check it out here. So here is it. The one is that execution, the performance is very, it will take very high, competition is very high.
Mm-hmm.
We have many, because many, I mean, the dimensions are columns. So just
Columns.
like whenever we have tree, the equation is like that, right? Sorry, this one.
Yeah.
Yeah. So if you have many variable x1, x2, and x6, so ultimately to get a target, we have like a dy by dx into x1 again plus dy by dx plus x2 variable. So these are the engine size and these are the columns. So every here is a variable value is there.
Okay.
So here it is showing. First one is y equal to mx plus c. So c plus dy by dx, then the variable dy by dx, again the variable. So that's how it will be doing for every column or features.
Yes.
So just like this one, dy by dx change in y when there is change in x, change in second variable, change in y when means change in target when there is a change in second variable, and so on for all the components. So that equation works like that. Right. So again, this is a regression problem. When there is a classification problem, so we do what? Correlation, right? So
Yes.
we do correlation. So that is how the competition is very high. And even training data set, X features, what you put, so is ultimately the competition will be high. That's why we require to be reduced. And when we reduce, we have to make sure that we are not going to lose information. So that means what? There is a, let's say 10 columns are there and we want, or let's say 1000 columns are there, we cannot do the analysis of 1000 and we, because of computation and we cannot create some graph. So we want to keep 10 only component or columns which have around 97% of the information.
Okay.
So idea is like that. The first component, so whenever you convert it using the equations, I'll show you down. So the component created will be known as PCA1, PCA2, and so on. PCA1 is the first component, and it has most of the information preserved. Like if you create a compressed file, the size is getting compressed, but the image information is not lost. If it is lost little bit, we cannot see it, right? So little bit will be lost because of the gray, I mean, the RGB value, but we cannot, I mean, it's negligible, correct? So, but the size will get reduced, right? So, image compression is works like that also. So, PCA is fundamentally a dimension reduction tool. Also, it can be useful for visualization, noise filtering. So, visualization is for to do the visual, I mean, make a 2D or 3D plot, and noise filtering is something we call as a noise is means what? That is, I mean, the data data that has noise means the data is not symmetric or normal data. The noise we can create also, we can remove also.
Okay.
And feature extraction. So for feature extraction and engineering, ultimately we are going to do for feature extraction. That means we'll get to know the most important features. I mean, we are going to create some PCA, principal component analysis, new features that is like you can say and inherited from the big data set of thousands of columns. So mostly we reduce into two-dimensional space.
Yes, right.
So at the moment I will show you some graph with, then your visibility will be clearer. Let's say we go to the first this one. So let's say we have a cell like this. So but we don't know what are the different types are inside. Based on the information of the cells, nucleus size, and other information. So there might be of different types, but we cannot identify we cannot identify at the moment.
Right.
So what we do actually, so ultimately how we can get it like this? Because in 2D plot we can see like this only one things, but we cannot visualize what is going on. I mean, and how is the difference? So what we can do is, let's say we have many cells. So ultimately it works like that. What I wanted to tell you that, let's say there are two cells like this, two columns. So the algorithm will take the correlations. This plot in this two, and this is what negatively correlated.
Mhm.
So when cell 1 increases, cell 2 decreases, right?
Mhm.
And cell 2 increases, cell 1 decreases, correct?
Mhm.
Right? Cell 1 is value is like in a particle.
Right.
So this way, when you see a graph like this way, you always call as a negative correlation.
Mhm.
And this way is called a positive correlation. This increases, that also increases. And this is also known as like this gene 1, let's say this one, gene 1 means this one first, 3 value.
Mhm.
Cell 1 has a 3, no, it's gene 9, sorry, gene 9, 0.4 and 3. So this is gene 9 and this is gene 1.
Right.
So this one is lowly transcribed in this area, in cell 1,
Mhm.
and highly dismissed closer to this axis.
Mhm.
So if there are 3 cells or 3 columns, so the works happens like this. So cell 1 and cell 2 comparison will start, then cell 2, cell 3, and cell 1, cell 3.
Mhm.
So to find out the relationship between each and every column, so this much of work happens.
Mhm.
So if there is like this increases, so ultimately exponentially the number of the combination of the dependency, I mean checking the correlation between each and every second features will also increase.
Mhm.
And ultimately we cannot put a correlation graph like this, and we cannot plot all the dependencies that cell 1 and cell 2, what is the information is there, and cell 2, cell 3, what is the information. We cannot put it like this.
Mhm.
So we cannot put it like this, right? So but there is a correlation is there. So every feature and every one features column and the other has a some relationship is there. How to represent that relationship? This is PCA. PCA can convert the correlation among all the cells into 2D graph. So after that, how it is correlate? I mean, it will correlate, and you will plot it with let's say different colors, and that will make you visualize these things into this one.
Right.
And we then identify the internal meanings of that.
Right.
And then if you see, we represent it in PCA1 and PCA2. Out of this, cell 1, cell 2, see here it is cell 1, cell 2, cell 3, and cell 4, right?
Mhm.
Correct? So there are many dimensions are there as per the number of columns. But when we go like this, we got the PCA1 in the X direction and PCA2 in the Y direction.
Right.
So this is the component. Actually, what it means, it contains the information of, let's say, this 4 or 10. Let's say there are 1, 2, 3, 4, 5. 5 cells are there. So these two X and horizontal and vertical component PCA1 and PCA2 can contain the information of the 5 cells.
Mhm.
So that is how it works. So the axes are this PCA1 and PCA2, these are ranked in the order of importance, means how much information it contains.
Mhm.
So that is like it will create some vertical. So it will create a new this one data set with PCA1 as the first column, PCA2 as the second column.
Okay.
After we apply, instead of cell 1, cell 2. So just for example, like say, so let's say we have to apply PCA. So in sklearn.decomposition import PCA. This is the header for scikit-learn for PCA. So PCA and components is equal to 2. That means we wanted to convert into 2 components.
Means
So
two
we
access.
want all the information of this variable x. Let's say there are 20 columns are there. So we want this information to be kept and show in 2.
Okay.
Then the two components may not be sufficient to give all the data, all the information of x number of features. So this is the way PCA and PCA.fit of x will ultimately result in this. So PCA has been applied. So, but how many components are required? So fundamentally, I'll show you now. So to visualize it, we'll look at some handwriting digits. So handwriting digits are 0 to 9 digits that are written was 0 to 9 digits in handwriting format. The useful of the dimension reduction may not be entirely apparent into 2 dimensions, but much more clearer when looking at higher dimension. So, like 2 dimension may not be enough to keep all the information. See, so sklearn.data sets import load digits. So this is the data sets which contain the many digits that are number only from 0 to 9 handwriting. Just like in paper, if I put 0 to 9, you write the 9 and I write 9, it will be little different.
Yeah.
So this data you can load it and you can see this. So this is when you load it and dot shape is reflecting 1797 handwritings of 1797 digits are there 0 to 9 and all the digits have 8 into 8 pixels. The block size is 8 into 8. I mean 64 dimension. So there is, so this is like every, let's say 0 to 9, any image is there, right? So if I put a 1, yeah, this is, so these are like this. Okay. So give me a second. Hello? Yeah, why you need? Pardon? No, it's already class is going on now. Okay, so see, these are the individual digits, right? So this every single requires 64 dimension, 8 into 8 pixels to represent it. So all these images, 1797 number of images are there between 0 to 9, and these all have 18 to 8 pixels. That is 64 dimension. And when we apply PCA, here we can put it project to how many dimensions? Project from 64 to 2 dimensions. So they are a little bit different. I will try to tell you. Generally, you are seeing all different features name, right? Name, age, or right? Is salary or something as a column name, right? That's the features, right? So here we don't have such a name. So here the 64 bit dimensions required to in a matrix to represent the image, and which is we are going to put into 2 dimension. So it is like somebody's paint is there. So I'm not sure. I mean, you clear or not? So just I wanted to
Sure.
show you, and like let's say this is a matrix. Matrix created, and this is 1 row, 2 row, and 3, 4, and 5. Let's say there are 8 is there. 8, and this way also 8. And so that means like this, correct?
Yes.
And now 9 is contained in here, right? So the 9 is represented by 8 into 8 pixel, and like that we have many of thousands of something images are there. So every image has how many columns? 64. I mean, 8 into 8 pixel is there to represent. So we are thinking like 8 into 8, 64 pitch, that is the individual pixels is a one dimensions or column features. So this is one feature, this is one feature. So we have 64. And that 64, if we wanted to reduce it only 2 in PCA, so we wanted to keep maximum information in it. That is like only 2 pixels to contain the maximum information. The digit 9. So, but we cannot do, we may require some 15 to 20, that we'll see how many components required, so that we can clearly, after that we can apply algorithm, and we do the correct calculation. So look at more, then you will be clearer on it. So after applying PCA on the digits, we said 64 dimensions, or so now has been converted into 2 dimensions. Okay. So PCA has been applied, and Nimsi, you were there. So we introduction of the PCA has been already missed, I think. So you can follow up from here. It's gone. So here if you see, after we convert it into 2 dimension using PCA, what we have to do, the PCA and the number of transformation we do. Generally, we do 2 dimension, 2 transformation, because that contains most of the information. And
But how did we, Jimmy?
yes,
Jimmy, how did we decide that only 2 dimensions contain all the data?
that is there is a pixels down. I'm going to hit it in some time, 5 minutes, I think. So then you'll come to know how much actually required. So 2 is not, I mean, a recommended way to find that there is a 2 component can contain most of the information that is to represent that. So this is a representation. So if you see here what we did, So we have applied PCA formula we have introduced here, and then the PCA objects dot feed transform on the digits data. Why did we use feed and transform? Just like the feed of the data we do, right, to train things. So whenever there is a change in the matrix, when there is a change in the matrix, we have to do feed transform instead of only feed. So you'll see in some cases, whenever you changes the data sets, the dimensions, then you have to apply feed transform. So what we'll do is like, it will do the calculations by bringing it to flattening the data, then again it reshapes to its original form. So here if you see, this is the data.shape, this is the original data, this is the original data, and this is the dimension, this one, and the projected is this one. Because PCA has been applied to 2 dimensions, so it is converted to 2. Now look at this one. So projected in the all rows with first component and second component. So because only 2 component is there, ultimately you can put more than that. And this is a scatter plot of the target. So it will represent 10 colors, 0 to 9. So how many types are there? Ultimately, we wanted to use 10 numbers to get CMFDC. We can put a type of coloring and all. So we can plot this in 2-dimensional space, and if you see the 2-dimensional space contain 10 colors, that means that the data are of 10 0 to 9 different digits. The 9 is this one, the range are 8, and that we are representing in the 2-dimensional space. So I think you are missing something, right? So it's little bit different. So down I'm saying how to find out how many components are actually required. Any questions on hello?
Actually, like I'm not clear about this.
Your voice is coming very slow actually.
I'm not very means I don't have a clear understanding of this plot which you did.
So
What were we trying to do here?
so this is, if you see, projected is PCA. PCA is right. This one algorithm. This is a one line is there. After we import PCA, so the program I will show you. Then we can do PCA.feed transform on the actual data. Then because we specified that we need a 2-dimension only, so it will automatically convert into 2-dimension like this. So 2-dimension means 2 only columns are there. So this is the first column and this is the second column.
Right.
In these 2 columns, we wanted to represent 10 different colors, 10 different types of data. And that data is what? Digits.target. So now I'll show you that the digits.target has all the digits. Let's see from the example. I'll go to the sklar.datasets import load digits, and then load digits if you print out. So this is the data. This is the data, and this the target has how many? 0 to 9. The target names are 0 to 9 only, and there are image itself are like this. So image will have ultimately the actual image, which you cannot be interpreted like this with a matrix. So this is one matrix, correct? So in between there is a dotted area, so which finish in between. So the image is represented by a matrix, so individual matrix. So the image you cannot find out like this, and the description of the data. So here, if you see, digits of target mean target of area of this 0 to 9. So if you see, there is a data is there and target is there, and target is represented by image. So, but this is the Excel form of digits, and this is the image of it. And here we plotted in scatter plot. We plot the in x and y direction, the x and y value, and then we plot the data. What is it we want to replace it? The different data. See the range of the different data. So we have 9. If you put 50, only one number, then it creates a one big number. So you put a 9 of the target, that means 0 to 9. So there are 9 different types, it understands. There is 9 different types. 0 to 9, sorry, 10 different types, and that will get into, from here, you get the color of 10. Now it's clear a little bit.
Yeah.
So 10 colors are, 10 digits are represented by 10 colors from here.
Okay, got it.
So, and that's presented in only 2 components. Now see, the question is this one, import numpy NP. So this is a PCA, how we can do. PCA.feed of digits.data. And PCA plot NP cumulative sum, PCA explain variance ratio. This is a inbuilt terminology of PCA. So what we plot is X level number of components and cumulative explain variance in the Y level. So ultimately, this is only we are putting this this one, the text only. I think from outside. So what we wanted to plot is plot of NP dot cumulative sum of PCA explains variance ratio. This itself will plot in like this, number of components versus number of explained variance. We don't have to rename to something different. So that's why we type like that. So what it means is the first 10 components contain 80% of the data. So these are the first 10 components. Out of the 64 dimensions, 10 components contain around 80% of the data, and 20% contains 20% number of components means the dimension you can take. Can contain how much variance is like a 90, right? So if you take 20 PCA, that means principal component, you can retain 90% of the information. And if you take 30 components, you can get 98% of the information. Understood?
Yes.
Yeah, so then here we can decide. So we cannot take 2 components for this kind of problem. So we are going to lose a lot of data. So might be you can take 20 or 30 to get out of 64, 30 components to get 98% of the data. So after we know that 30 components is required to retain most of the information, what we can do is, so here we can change it. So this is the header, right? Scalar decomposition import PCA. So you can change it to 30. So then PCA.feed transform on the data, and ultimately, if you run, it will be converting into 30 components. So now we have changed it to 30 components. Looking at that, we wanted to keep the 98% of the data. We keep 98% of information with 30 principal components. Okay, so this is the idea actually. So then what we did, target ultimately it's the same only. The representation what I showed you with the PPT is ultimately we are trying to produce in the experiment method. So if it is clear, then I will move to the another example now.
One question.
Yeah.
If the 30 dimensions were needed, we're going to explain 90% of the variance, and we use only two.
Yeah, the voice is, can you be louder?
Yeah. What I'm saying is that if 30% of the 30 dimensions are needed to explain 98% of the variance, we use two. That means we are not using.
Somehow, I don't know, the voice is almost nil from your end.
What?
Your voice is going exactly, I can't hear you again.
Okay. Are you able to hear me now?
Again, it's gone.
I don't know.
Can you type it here?
Yeah. Where do you want to type it? How do I access the chat? It's showing us.
Pardon?
You're saying you're asking me to type in the chat, right?
Yes, yes. Now I can hear you. Now, whenever you're speaking, it's going down almost nil.
Okay.
Now
What
I can
I'm
hear you.
saying is that, yeah. What I'm saying is that, like, if these dimensions had 30 dimensions were needed to explain 98% of the variance, and we used only two, that means we are underrepresenting the data, right?
No, again, it's gone. When you continuously speak, then again it's very low.
Okay, let me send you a message.
Okay. I mean, you can type it if it is. I mean, it takes you 1 minute. Just can type it, so I will explain you. So, are you typing on the chat?
Yes. I send you in WhatsApp.
Okay, once again.
I send in WhatsApp.
Yeah, if 30 dimensions are needed to explain 98% and we use 2, then it indicates that we are not using the right dimension to use the PCA. Is this correct? Yes. So that's why the explain variance ratio we are checking. So what it means that two things is there. First of all, the 30 components are required to keep most of the information. But can you see first here, if you see the 10 components can keep 80% of the information, right?
Yes.
So 20 components can contain 90, yeah, more than 90% of the information. So if you keep the 20, then you will getting the 90% of the information. 10% will you get lost. So that is, it is explained. So based on that, so it's recommended that you should keep 20 to 30 components. And I will show you on where we have already transformed data out of many. So uh, so generally we'll be using which one is gone, movie data. So we'll be using PCA along with other algorithms. So PCA job is to reduce the dimension, and then we have to use algorithms. So it is not a supervised, it's unsupervised algorithm because it doesn't work on predicting classifying something. So, but then what we'll do? So this is, let's say, one example, but we are going to use after we understand this data. So I wanted to show you some data, which is financial data already where I kept it. So it's a very big data set. It's already transformed. Yes, I remember fraud analytics data. So the data set is here only somewhere. So generally we apply PCA, and after that we apply some algorithm. So like what I'm saying. So if you have a data and if you have a target, let's say classification problem, and you know that like you can use KNN, or we are going to like SVM, support vector regression, support vector classification. So classification problem can solve and find out the accuracy in kind of data. But then let's say we are interested because of the column names are very big. I mean, there are many columns are there. So then what we'll do, first we have to apply PCA, and then after that we have to apply other algorithm. PCA itself will not give you anything, but only it will reduce the data. So I had some fraud analytics data. Let me check if it is there. Otherwise, in the next class I will show you that. Fraud data has been already because of which because the financial data cannot be shared outside the bank. So in Kaggle, somebody transformed it by taking authorization. It transformed by using PCA and then shared to general public, so that nobody knows what talks about which column, because the column names are getting changed and data is reduced. So actual data is not shared, but it is using PCA. It is reduced to some 500, 600 columns. Yes, this one is the data set. Oh, the program itself is here. Okay, wait. This is the credit card fraud detection. Okay, wait. So in eDrive, it's so see this is the data. You can see all these column names as V1, V2, right? So this is the data, what I'm talking about. You are there, Amit?
Yes, I am here.
Yeah. So see, this is 28. This is already transformed using PCA. So
Right.
yeah, if you apply PCA and after that you plot, after that is provided a name. So any data you can take and apply PCA, and after that you. So if you see that only the data will be like this. So like what we did is handwriting disease, right? So here. This is the data.shapes. Import pandas as PD. So this is a 64 columns, right? See, this data has been represented like this. So this is, you cannot, based on this you cannot find out. Based on this only one information is been shared. So this is 0. Some other, binary values are here. So just wanted to tell you how it is getting changed. So so instead of digital data, our data will be projected, right? So this is the new data. So we have how many components we keep? So around 20 to 30 components I think we kept. So these are 30 components, right?
Yes.
So similarly, this has been shared like this. So this is 28. Might be there are 1000 columns are there. It has been first transformed, then and after that, this is some real-time data, and then it's shared. and the data is like that. If it is 0, that means fraud is not there. If it is 1, that is the fraud has been detected. So here it is all showing 0. So somewhere it will be 1. So because see number of rows records are very high. If you see here, if you see 2,84,000, right? So in some cases there will be fraud is there. When is the fraud is there, it will be 1. So based on the fraud detection, it's a binary problem again. So you can say, but I think it's used for using linear regression or what model I have used. Yes, it is solved using linear regression. Sorry, neural network. So this is used using, you've seen the dense deep learning we've used many layers, and ultimately we solve it with accuracy of 99%. So it is just to show you the data that PCA is going for a transformation. Don't think that PCA is again an algorithm for doing something. So in case the data was given you the original data, what is your job would be? Look at the number of features is more than 1,000. What you would do it? Do it the same thing here. Finding out, applying this and get the explain variance ratio and take that much of features and then plot it. That you can do, right? At the moment now, if you want, right, with the help of this, you can do it, right? So this is projected. So any questions on this one now?
No, it's okay.
So the basically is we after transformation. So after this transformation is done, so here it is done decomposition. So PCA applied and feed transform on the original data.
Right.
So then the thing is the projector you will get. So that is will be our data now in the data frame we have loaded. So from there onwards, if you see again, then we have to do something, right? So it might be a problem of classification or the target is not there, we have not printed out. So then will be the problem will be like this only. It will be either a regression problem or it's a classification problem. How will you get to know? By looking at this target, right? So the explanation will be also there, and you can put a count plot to get to know how many variables are there in this class, right? So if you put a count plot, when you see this, will show you. The count plot means, if you remember, we did it in logistic regression to see the number of variables, 0 or 1, how many different targets are there.
Right.
So that's how I mean, you can find out this class. It's a binary problem or multi-classification problem or what. If it's a regression problem, you get to know by the index only, the price or what. Or right, so some values will be there. It's a continuous value. So yeah, so after PCA we're going to do apply this PCA in other algorithm. So let's me now. Yeah, so I'll be showing you dimension reduction. Yeah. Okay, somewhere it's a three-dimensional diagram is also here. Let me see. Reduction. So here if you see, it's a 3D plot. 3D plot done. So 3D plot is done means at least 3 components is required to show. But three PCA component, then you can show it like this. But 2 components we are suppressing it. So ultimately, what happened? All the things that is in the different plane, ultimately we suppress it in 2D. So this is something control plus. So ultimately you can visualize this. So all these things, if you put it suppressed from the app and keep it all this in this plan, then will be in the two PCA, PCA1 and PCA2, you can keep all the information. Like the yellow will also come there and red will also come. Everything will be merged in this plan only. Now have a clear? I mean, it makes sense now.
Yes, that's correct.
Yeah. So this is have to suppress like this in the this plan. That is the concept. And just to represent in the two dimensions. So we are taking more PCA than ultimately, so we cannot represent more than 3 dimensions, but ultimately it is, I mean, you can assume that in 4 dimension also, 4 components can present. So PCA can be 10, then there are 10 dimensions and that is plotted in different dimensions. So in PCA2, all the information will be like this, different colors will be mapped in here. So there are some more theories that I'll quickly tell you that eigenvalues and eigenvectors. So this indicates how transformation happens in images. Now we have seen that we have transformed, right, 64 dimension to less dimension. So what is the maths behind it? So eigenvalues are special set of scalars associated with a linear system of equations. So there are 2 dimensions coexist, eigenvalue and eigenvectors. So if there is a matrix like that, K into K matrix, so K, I mean, it's a square matrix, and eigenvalue lambda will be like this. This is a constant that is called eigenvalue. And the equation will be like this. So if you see this diagram, you'll come to know how it is. So here it is this is the, I mean, let's say pixels where we put a image. Now we are going to transform the image like this. We have transformed it in the right direction. So what will happen, if you see, this will not change the direction. And this, which are not going to change the direction. So this, this purple and blue are not changing the direction, but the reds are changing the direction. The vectors in red are not parallel to either eigenvector. So these are the direction of eigenvector. So in this direction and this direction, the perpendicular, the direction of plane and the perpendicular direction. The blue vectors after the transformation are 3 times the length of the value, actual value. So eigenvalue is 3, while the length of the purple are unchanged. So if you see the purple are unchanged, so it is same. But the blue are transformed because and the length has been increased 3 times. So eigenvalue is 3. And eigenvectors are those who does not make change in directions. So the reds, if you see, they change the direction, right? The red arrow, you can see the change in direction from this one. So that's why these are not eigenvectors. So eigenvectors are those when we transform the image, it's not going to change its direction, but the value can be changed. And the value has been increased to 3 times, so the eigenvalue of the blue is 3, and this is 1 because it does not change its length. Understood, right? Amit, any questions on it?
So like you're saying that the eigenvectors will be those like whose are you able to hear me?
Yeah.
So eigenvectors will be those like where the arrows don't change, right?
Yes, the blue arrow, if you see here, is in the eigenvector because it doesn't change the direction. Here, if you take 2, the red is changing its direction. So this is not eigenvector. The
But
blue,
the blue is.
after the transformation also, it is pointing the same direction. So
Okay.
it's eigenvectors. So eigenvector and eigenvalue are associated. If the length is going to increase because of the transformation, so
Right.
the number of times the length is going to increase is the eigenvalue.
Oh, okay.
So the blue can in the blue it can be eigenvalue, but this is not eigenvector, red one.
Yeah. But the eigenvalue, but the eigenvector will increase in length by the eigenvalue. Okay. That makes
Yeah,
sense.
eigenvalue is the change in length of the eigenvectors when we make a transformation. So actual mathematics is like this. So we were talking about the transformation using PCA, and when we the dimension has been reduced. So think of it now, it contains an image like that, and we have transformed. So then ultimately it will go in the back, and the these equations will get to work. So if A is a matrix, A of x bar is equal to lambda of x bar. This is the equation. So A minus lambda I, so it's taking in the left hand side, into x bar is equal to 0. And A minus lambda I is equal to, both are 0, that means, right, product. So that means we can say this is equal to 0. And using this formula, A minus lambda is equal to 0. If you put in this equation, it will be like this: 2 minus lambda I. 2 minus lambda. 2 minus lambda will be there. I is considered 1, I think, here. 2 minus lambda 1 only is indicated, not sorry, I is 1 only. So 2 minus lambda, and this equation has been transformed as per this one: A minus lambda bar is equal to 0. And this has been this is, if you see the determination, 2 minus lambda into this determination of this minus 1 minus of 1 into this one, right? This and this one.